Hello, Namaste. Welcome to this channel, Dr.ARM'sChemistry. Chemistry. Friends, we were discussing the electronic spectra of transition metal complexes, and in that case, we have seen last time the D2 configuration. For which we have seen the how to obtain the terms for this G2 configuration. Now we will see the forbidden transitions. In the same case, we will see the forbidden transitions. In this D2 configuration, the terms arising are D2 configuration. The terms arising are one, the ground state, triplet F, and second, excited states 3F, 3P, it is triplet P, singlet D, singlet G, and singlet S. So these are the singlet states. So these are the excited states. Ground state, F contains, this 3F contains 2 electrons with parallel spin. And this is because the spin multiplicity is 3, whereas these states, this is also a triplet state. This is triplet state, and these are the singlets. So these are having the 2 electrons. There are 2 electrons with spins pair. And therefore we can show that the transitions from the ground state, these the transitions. So we will show this in the diagram. And this is 3P. So here the 3F splits into 3 energy levels. 3 energy levels. And this is the 3 T1G F. This is 3 means triplet T2G, and this is A2G triplet A to G. And the P state is not split. The P state is not split, but it is transformed into the triplet T1G. Triplet T1G. So this is represented in this way. Now, when this electron from this ground state, one of the electrons, there are two electrons, so one of this electron is moving or excited to this T2G state. Then in this way, here into the T1G to this T1G, and therefore third state is also excited. So you can show this from this T1G to this A2G state. So the ligand field strength increases in this direction. Ligand field strength increases in this direction, and we can show that these transitions means there would be the 3p and 3f states shown here, but the 1d simulate d, g and s states are not shown because these are forbidden. Why? Because the electrons in the 3f and this 3p, these 3f are parallel with parallel spin, but these three states are having their spins parallel, and therefore the state means excitation from this 3f to these states involves the spin pairing, and therefore these are very weak interactions between the spin and orbital. That is, the spin interaction with the orbital interaction is very weak, and therefore it is not involving absorption of more energy. So the interactions are weak in these simulates, and therefore these states are called spin forbidden. So these states are called spin forbidden, means not allowed. But the transition from this, that is 3f to 3p, is allowed, or these we have shown here that the transition from this T1G of this f to this T2G of f, that is triplet T2G, or this triplet T1G and this triplet A2G are allowed. So three transitions are possible here. Here the p orbital is not split, but the f orbital is split into three states. P orbital remains unsplit, so it is shown in this way. But 3p triplet f is split into three levels. So these are the levels T1G, T2G, and this here A2G. So these A2G, T2G, and T1G are the energy levels after splitting of this F substate, that is F state. Similarly, octahedral field, the P state is not split, and hence it is simply transformed into this T1G. P remains unchanged, and because of this we can observe these transitions are shown in the form of absorption bands like this. So we can have these. The energy is 40,000 per centimeter, then 30,000, then it is 20,000, 10,000, per centimeter, and we get this absorption band in this. Like this. So we get these two absorption bands. So these are having the absorptions. So this band, first band, shows absorption due to the two transitions. That is the highest energy transition. So this is the highest energy transition from triplet T1G to this triplet A2G, and this is more intense band. So this is shown as triplet T1G, F2, triplet A2G, triplet A2G transition. Similarly, there is another transition, second transition, that is this triplet T1G 2. This triplet T1G, triplet T1G to triplet T1GP, that is which is arising from this 3p state. So the level arises here and the transition is second. So this is say first, second and third. So three transitions are shown here. So these two bands are arising here, and third band is arising which is of lower energy. So that is represented as 3 T1G F2 is 3 T2G 3, that is triplet T2G of F. So this involves the transitions. These two transitions are shown here because these are high energy transitions, and the second one is relatively low energy transitions. So these two transitions, these two levels, that is 3T1G and this triplet T1G and triplet A2G, are lying above this crossover. This is crossover of P. Crossover of P. So these transitions are important and they are shown with this absorption band. So we are showing here the two transitions, that is 1 and 2. That is 1 and 2, and this is shown by the transition number 3. Then, in order to interpret the spectra of a D2 complex, we can consider the example of this another example. So interpretation of spectra for vanadium H2O6 3 plus. This is also the example of D2. This is also D2 configuration, and there are two. We have seen in the diagram the two peaks are observed in the spectrum and the ligand field. Here we have to remember that this H2O is weak field ligand. Weak field ligand. The water is a weak field ligand, and the transitions are occurring close, as we have seen in the earlier spectrum here. The transitions are occurring close to the crossover we have shown in the diagram point. Therefore, the triplet T1GP and triplet A2G are levels, and hence these two transitions are not resolved into separate peaks, because the transitions here, the ligands are weak field, and these two transitions we have seen that the triplet T1G and triplet A2G, so these are lying near crossover, so there are no separate peaks observed. The vanadium 3 plus ion is complexed with different. Now if this ligand is complexed with other ligands, if other ligands are present in the complex, then the ligand will show the 3 peaks. If other ligands are, say, stronger than this, then it may show 3 peaks in the absorption spectrum. So in this way we can resolve these absorption spectra on the basis of the strength of the ligand or ligand field. Then another important case is the D8 configuration. D8 configuration. D8 configuration. For example, nickel complex. That is NiH2O 6 2 plus. NiH2O 6 2 plus. That is here the 3p state is not split as we show here. We will show this in the diagram. So first of all, we will show the electronic configuration. So here these are the triplets, T2G levels, and these are EG levels, EG, and these are T2G levels. So we have shown the electrons. There are 8 electrons. So these electrons are shown in this way. This is weak field ligand. So 5 electrons, then 6th, 7th, and 8th. This way there are 8 electrons distributed. Now there are 2 holes. These are holes. These are holes. So there are 2 holes in the EG level, as we have seen here, and during the excitation, so after excitation, the electrons can move from this T2G to this EG. So electrons are moving say this electron is moving here and this electron is moving here, then so this will require some H nu and H nu we will see, and we will get this new excited state configuration where the electrons are distributed like this. So two electrons are moving with here opposite spins. So out of these 6 electrons, 2 electrons have moved in the Eg level and the holes are moving in the T2G levels, and therefore we can show that the hole is transformed. Hole is transferred from this Eg level to this level. Holes are moving from these two levels. So these two holes are moving here and electrons are moving in or excited to higher energy level. So the promotion of two electrons takes place with the transfer of two holes from this Eg level to this T2G levels. Then another diagram is required here. So we will show this diagram. So we are having here the triplet F and the triplet P, and the ligand field strength increases in this direction, increase in this direction, and as we have seen that the F state is split into 3 levels, but the P state is not split, it remains as it is, but it is transformed into the corresponding energy level T1G. So we will show this splitting. So this is the triplet A2G. So if we see the previous diagram for our D2 configuration in case of vanadium, so you will find that here this state is different, that is inverted. So this is the triplet T2G and the triplet T1G, triplet T1GF, whereas this triplet T1G of P. So this P state is not affected much more by the ligand field strength, but this F state is affected and it is inverted. So during excitation, the ligand field shows that the states are inverted. So in case of vanadium, that is, it has shown that the T1GF is ground state So this is ground state. So we have shown that this is ground state. So in case of previous diagram, that is in case of vanadium, the ground state was here at 888F T1G, and the excited state, that is A2G, is much higher than this 3P, which is transformed into this 888 T1G of P. So here the excitation is not much stronger here. This will show that the P state is not split and it is not inverting. This P state is not split, so there is no question of inversion. It remains the same, but it is simply transformed into the triplet T1GP. But this F state compared to the previous case is changed, is inverted. So the A2G level comes down, and this T1G, which was the ground state in the previous case, is coming at the excited state, that is highest, that is high energy level. So thus the ground state term for Ni2 is 3A2G. So this ground state is 2A, this triple degenerate A2G state, that is triple A2G. In both D2 and D8 configuration, the ground state is 3F. Here the ground state is 3F, that is triplet. So we will show this in absorption diagram. In case of, if we show this in the absorption, so these are the scale is shown as 30,000, so this 20,000, and this 10,000. So we show this 10,000. Now, in this case, the peaks corresponding to these transitions. So we will show that these highest energy transition is from this triplet A2G to this T1G. Then we will have the second transition arising from this triplet A2G to this triplet T1G. Third transition is arising from this triplet A2G to this triplet T2G. So we are showing these transitions here in this diagram as the graphical representation. So you will find there are three absorption bands corresponding to these three transitions. So this stronger band is arising due to this transition from triplet A2G to this T1G. So we will mark this as 1, 2, and this as 3. So we will show this here strongest band, that is triplet A to G of F, triplet A to G to triplet this T1G, triplet T1G of P. Then second one is here triplet A to G. So this triplet A to G to triplet this T1GF, T1GF, and the third is shown here, triplet A to G to this triplet T to G, triplet T to G. So these absorption bands are corresponding to this first, second and third transitions. So we have shown here frequency. Here this is frequency A per centimeter, and here the epsilon, we can say the molar absorbance is shown on this side to obtain molar absorbance is shown here. Ground state, as we have shown here, this is triplet A to G. In both cases the ground state is same, but it is low energy. Ground state is low energy, and in this way we can show that the transitions corresponding to these states are clearly separated by the three absorption bands. This is because the splitting and inversion, splitting of the 3p state, no splitting and no inversion of this 3p triplet P state, but this triplet F state undergoes splitting into three levels and inversion of the states also, that is levels also. So in this way we can explain this D8 configuration. So we will stop our discussion about these various states, and we will see the next part of this electronic spectra in the next lecture. So please subscribe to this channel and press the like button and bell icon also. Thank you very much for watching.